All right, hi everyone. Welcome to the first video for what's considered week 4 for statistical models. Today we are moving on for the first time from simple linear regression, and we're going to be talking about multiple linear regression. So this is an extension, generalization of simple linear regression. We're just moving on to the case where we have more than one predictor variable now. So in week 4, which will be split up into 2 videos, as per usual, we're going to talk about the multiple linear regression model itself, how to assess assumptions for this model and see if it's appropriate for a given setting, how to compare 2 different regression lines, and then also how to construct or build new predictors from old ones, which sometimes is called feature engineering, depending on the field, or data transformations. So first, we're going to recall back to simple linear regression and when this is useful. So this is the case in which we have one quantitative response variable, which we denote with y, and one quantitative explanatory variable, x. And we're modeling the linear relationship between those 2 variables. So as a quick reminder, quantitative means that arithmetic makes sense when doing this on these variables. In other words, we can add and subtract, divide and multiply, and these are sensible things to do. So for example, your major in undergrad is a categorical variable because you can't really add, say, a math major and a economics major, or a journalism major and an English major. You can't add those things together. But you can add people's GPA. If a student has a GPA of 3.5, another student has a GPA of 2, you can average those out, which is like 2.75 if you look at the average of those 2, if you add them and divide by 2. So GPA is a quantitative variable. Your major in undergrad is an example of a categorical variable. So we cannot use major directly in simple linear regression, at least not yet. We'll talk about ways we can incorporate this later. And recalling back to simple linear regression, we had some assumptions that were necessary for our model to be valid. So specifically, we assumed that the residuals or errors are independent, that they have constant variance, and that they are normally distributed, that they follow that typical bell curve that we see in statistics show up a lot. And actually, all 3 of these assumptions can be summarized and stated in this one statement here. So this is saying the errors epsilon are distributed independent and identically, IID, normal. That's what this sort of special case n means. Normal with mean 0 and standard deviation sigma sub epsilon. So this is saying they all have the same standard deviation, which means they will all have the same variance. So sort of this is a way to succinctly state all 3 of these assumptions. Now extending this model to multiple explanatory variables, we're moving on to multiple linear regression. And so specifically, instead of just a single x, we have, say, x1, x2 through xk, where k is our number of explanatory variables that we have now. So we still have n observations for our data set, or n data points, but we have k explanatory variables or features measured, as well as a response variable y. So for example, we could model students' height, try and predict their height using their age and BMI. So height is our response variable in that case, and we have 2 predictors, their age in years, which is quantitative, and BMI, which is another quantitative explanatory variable. So we can use these together jointly to make a prediction. So our model statement looks very similar to the simple linear regression case. So we have still y equals the intercept term, beta 0, plus beta 1 times x, and then now we just have additional terms added on prior to the residual at the end here. So each x gets its own unique beta, and they're just multiplied by each other here, so the order does not matter. And then we still just have an intercept term and the residuals in the end. So this is the theoretical model that we're assuming holds true by fitting a multiple linear regression model. And similar to before, the assumptions are pretty much just regarding the errors, along with the linear relationship between each predictor and the response variable, x, j, and y. We make all these assumptions about the residuals or errors. So conveniently, we still get just one set of errors. We have n errors if we have n response values. So it's not like we have to check the errors for every single predictor individually. It's just jointly for our model. Our model just has one set of errors. So the same as before, we're checking if the errors are independent, if they have constant variance, and if the errors are normally distributed. And to check the linearity assumption between each x and y, we would just want to create a scatter plot for each corresponding pair. So if we have k explanatory variables, to check this linear relationship assumption, we would need to look at k scatter plots between each x and y. So for simple linear regression, we had 3 total parameters that we needed to estimate: the intercept term, the slope, and the standard error of the regression, the standard error of the regression squared, actually. Now we can think about, with k predictors, how many parameters are we estimating now? And one way to think about this that might be helpful is that simple linear regression is a specific case of multiple linear regression with k equals 1. Okay. And so for simple linear regression, the number of parameters equals 1 for the intercept, 1 for the slope, and 1 for the standard error of the regression. That's how we get to 3. For multiple linear regression, the number of parameters equals 1 for the intercept term still, but now we have k slopes we need to estimate instead of just 1, and then still just the standard error of the regression. So now we have k plus 2 parameters that we're estimating for the multiple linear regression model. And again, simple linear regression is just a specific case where k is equal to 1. So we had our theoretical model that we're assuming before that has the epsilon or error term added on to the end. Our estimated model or prediction equation is given here, where we denote y hat as our predicted response value, and it's equal to this linear combination of the x's, where we estimated the intercept term and the coefficients for each x, the slope for each x. So again, the hats denote that we estimated these values based on our data set. And the x's, we just use the actual observed values in our data set. To find these beta hats that we use for this model, R or other software minimizes the sum of squared errors again using calculus. But I'm not going to expect you guys to do that in this course, but it's still good to understand how that's working exactly. Yeah, so the SSE again that we're minimizing, or that R is minimizing to find these regression estimates, is given by this formula where we sum n squared residuals, where specifically the residuals SSE equals the sum of each residual squared. That's what this is equal to up here. So each one of these is a residual, which equals the sum of each actual response value minus the predicted response value squared. So the square is inside the summation. We square each term individually and then add up all those squared terms. You'll notice if you tried to sum all the errors sort of on the inside and then squared that quantity, you would always end up with 0. And that's because the sum of the residuals for simple linear regression by construction, the way the model is fit, is always 0. The errors always sum to 0. So we have to square each term in the summation individually. And the predicted response value, again, is given by this linear combination of the x's in our data set. And here the subscripts are, the first subscript on the x is denoting which predictor it is, the kth predictor or the first predictor, and the I is subscripting which observation it is. So this is for the ith observation. So similarly, for SS model, sum of squares model, we calculate this as the predicted value minus the mean response, and then squared again for each term of the summation. Where y bar, the sample mean response value, is calculated in this way again. We sum up all the response values and divide by the number of observations in our data set. And SS total, similarly, we do the actual response values minus the mean response value squared. So SS model, again, is representing the total variability explained by our model. And SS total is representing the total variability in the response variable. So the standard error of the multiple linear regression model, sort of an extension of what we saw before again for simple linear regression. So now it's equal to this, this quantity over here, the square root. And specifically, you'll notice that this is the same formula as before, except before we just had n minus 2 in the denominator. And so that's because, again, for simple linear regression, k equals 1. So before, the denominator was equal to n minus 2. And now more generally, for multiple linear regression, it's equal to n minus k minus 1. So just like with simple linear regression, we have an ANOVA table again, an analysis of variance table. And this is useful for testing our overall model and describing the amount of variability that we're explaining with our model. So again, this is a generalization of the simple linear regression ANOVA table, except we have k instead of just 1, so it's more general. But we still have these nice relationships in the table in that the model degrees of freedom plus the error degrees of freedom is equal to the total degrees of freedom. So n minus k minus 1 plus k is equal to n minus 1. And similarly, SS model, the sum of squares model, plus the sum of squared error, SSE, is equal to the SS total. And then to get our F-test statistic, which we use for testing our overall model, we calculate this ratio of MS model and MSE. And again, this F is useful. This F-test statistic is useful for testing the overall model, and it's called an F because it follows an F distribution. And this has two degrees of freedom associated with it. A numerator degrees of freedom, which is k in this case, the number of explanatory variables, and a denominator degrees of freedom, n minus k minus 1, where n is the number of observations in the data set. So when I say testing our overall model, this is referring to testing if the set of slopes, the set of regression coefficients, are all simultaneously 0. Versus the alternative hypothesis, which is that at least one of the betas, one of the true slopes, is non-zero. And so to test this, we're going to look at the p-value for that F-test statistic, which R will give us. So moving on from the ANOVA table, another aspect of multiple linear regression that's important is that we can build or construct new features or new explanatory variables from the ones recorded in our data set. So for example, if we have a variable, explanatory variable x1, maybe we think y, the response value, is related to x1 squared. So if there looks like a parabola, a sort of curved relationship in the scatter plot, that's when we would consider this transformation or using the squared explanatory variable as a predictor in our model instead, potentially. And so actually what we do, we don't just have a simple linear regression model, usually where we just have the squared x1 instead. We can have both terms. So we have our first predictor is just the regular old untransformed explanatory variable, which will denote x1. And we actually add on a second explanatory variable, which is the transformed x1. And that gets its own regression coefficient, even though it's a function of x1. So you can think of it as just being its own predictor, its own new column in the data set. But it's actually just a function of x1. So this is our assumed regression model, which they call in the textbook a quadratic regression model. So let's consider an example here where we use this. So we're looking at this Framingham heart study data set, which is another longitudinal study in that they recorded measurements on people across time. This was somewhere in the East Coast. I can't remember. I think maybe like Massachusetts or something. And they followed these people for many, many years, like decades, I think, recording these variables across time, these public health variables. So we're going to just look at these person's age and their systolic blood pressure to start. So again, you can use just the regular plot function in R. Here's some ggplot code, which is another way to create a scatter plot in R. I suggest you do whichever way is more comfortable for you. And I added a theme this time because you can customize your ggplots with a theme pretty easily in this way. So that's kind of what makes it more fun or exciting, I guess. Yeah, so looking at a scatter plot of each person's age in years and their systolic blood pressure measured in millimeters of mercury. Notice I put the units on the plot. That's always good to do. We see the relationship looks somewhat linear. It seems like a a positive relationship in that as age is increasing, people's systolic blood pressure is increasing a bit on average. There's sort of a upward sloping line a little bit if we imagine that getting fit through. But linearity certainly seems fine here. This point is a little bit concerning, this data point, but it's a pretty big data set, so hopefully this won't affect the results too much. I don't think it will. I think there was like 4,000 data points or so in this data set, so quite big. Looking at another scatter plot, I also created one by looking at BMI on the x-axis here, and then systolic blood pressure on the y-axis again. So here we certainly see a positive relationship between BMI and systolic blood pressure. So again, that means as BMI increases, systolic blood pressure tends to increase on average for people, it appears, which is sort of an intuitive result again. People with a higher BMI, we'd expect to have a higher blood pressure on average. So this is where multiple linear regression is coming into play, because we sort of have two variables that seem to explain blood pressure a bit, age and then also BMI. So we want to use them jointly together, not just fit a model for each one. So to do that in R, we use the LM, the linear model function again, and we're going to model systolic blood pressure as our response, tilde, and then our explanatory variables, so age plus BMI. And then we can view the regression output using the sum function from the JTools package. So looking at the regression output here, we can see that the coefficients for age and BMI are positive here, which is supporting that what we saw in the plot, that there appeared to be a positive linear relationship between age and BMI. And here again is the number of observations, N. So here it's 4,221. Here is our R squared, or coefficient of multiple determination, they call it. And we'll interpret that later in a bit. This is our standard error column. So here we have the standard error for the age explanatory variable, standard error for the BMI regression coefficient, their Ttest statistics, and then the last column is their corresponding p-values. So a lot going on in this plot again, as always. But fortunately, it's in the same structure as before. So just like before, we want to check to make sure the regression assumptions are met. And the best way to do that is to use plots. So we're going to just use the regular plot function in R, since it produces some nice residual plots by default when we input our model fit object here, which I called linear fit. So looking at the first plot, this is a residual by fitted plot. So we use this plot to check the constant variance assumption of the residuals and also potentially independence of the residuals. So first, with constant variance, again, we want a even scatter vertically of the points as we move from left to right on the x-axis across time, across the x values here. So it looks like there's no like fanning sort of shape, anything like that, where it's like smaller spread to getting wider. It looks fairly consistent across the x values. So here I would say constant variance appears fine. It appears to be met. In terms of independence, again, what we're looking for here, this plot can tell us if it's violated, that assumption is violated, but it can't really tell us if it's met for certain, because there's other ways it can be violated that can be than can be displayed on this plot. But in terms of independence, what we'd be looking for is some sort of functional form or some sort of clear pattern in the points on this plot. That would be when independence is potentially violated. So maybe like an oscillating pattern or a U curved shape overall, but we sort of see this just cloud of points. So that supports the notion that independence of the residuals is met here. So for checking normality of the residuals, again, we can use a histogram or a normal QQ plot, a normal quantile plot. So for the QQ plot, what we're looking for is if normality is met for the residuals, the points will all pretty much fall on this dotted line here. And so that's the case for most of the points to start. Those look great. Here we have some concern in that the points are sort of drifting up away from our dotted line. So, and then R even by default will tell you these potential outliers. It gives you the observation number, the row number in the data set where this point is recorded. So here we have some potential outliers in our data set as well. So yeah, based on this plot, normality is a little bit questionable just because we have these points straying pretty far from the dotted line here. Although overall, given the size of this data set, that it was 4,000 observations, that's quite large. And the bigger the sample size is in general like that, the more robust or resilient our model is to misspecifications of these assumptions. So since our sample size is so large, this seems okay here. The larger your sample size, the less of a concern the normality assumption is in general. So again, for multiple linear regression, just like simple linear regression, we can test the relationship of the response with each predictor. So not only can we test the whole model jointly using that F-test from the ANOVA table, we can also just test one predictor at a time. So to do that, for example, if we want to test its age is linearly related to systolic blood pressure, we can test these corresponding null and alternative hypotheses. So the null hypothesis here is stating that there's no linear relationship between age in years and systolic blood pressure in millimeters of mercury. And the alternative hypothesis is that there is a linear relationship between age and years and blood pressure. So recalling back from the model output, the T-test statistic for testing this, if we scroll up, we have for age, the T-test statistic is 26.015, and it has a p-value of rounded down to 3 decimal places at 0.000. Again, the p-value will never be exactly 0, but this is just rounded to 3 decimal places. So we have a p-value of about 0, a T-test statistic of 26.015, and since the p-value is less than 0.05, we say we reject the null hypothesis. So interpreting that in the context of the problem, we say we have sufficient evidence that age is linearly related to systolic blood pressure in millimeters of mercury. That's how we interpret the result from this hypothesis test. So we can also construct confidence intervals. Not only can we do hypothesis tests, we can also do confidence intervals for these regression coefficients. And so this is again where we'll use the standard error estimates from the table. So this is the standard error of the estimated coefficient for age. From R, from that model output, we see that 0.035. And our point estimate, our estimated slope again for age is 0.910. So to make a confidence interval for this regression coefficient, we use this T-star multiplier, which I will always give you guys. So in this case, using R, I found that it's 1.96. It's nearly always about 2. And thus, the confidence interval is given down here. So I plugged in the estimated regression coefficient, T-star multiplier, times the standard error of the coefficient for age. And then you should get these two values when you do that. So it's good to know how to create a confidence interval like this given the regression output here that I gave you. So we can also add a quadratic term for age here, in that we're adding age squared to our model. To do this in R, we're going to, so we have age plus BMI plus, you might think we can just do age caret 2, age squared. But R likes you to wrap, when you have like a function of an explanatory variable, R wants you to wrap that in this I function, which I believe stands for inhibit. It's sort of telling R, like, it's just letting R know you have a function of an explanatory variable, so it needs to like make this column beforehand and then input it to the model for you itself. So it does a lot of work under the hood for you, which is nice. But yeah, so here we're modeling systolic blood pressure of people using their age, their BMI, and their age squared, because maybe we think for some reason there's this quadratic relationship between blood pressure and age. And again, we can get the regression model output for this corresponding fit. So we'll continue talking about this next time, but that's it for this video. So thanks, and I'll talk to you guys again soon.